Unearthing gold. A deep dive into orogenic gold deposits. Gold remains a crucial financial commodity and is also essential for industrial applications like electronic components and medicine. While gold occurs in diverse geological settings, understanding its deposits can be complex due to the dynamic nature of Earth's crust, which often leads to overlapping and overprinting deposit styles. Among the various types, orogenic gold deposits have historically formed the majority of economic gold deposits, alongside placer deposits. They form during compressional to transpressional tectonic regimes, commonly associated with convergent plate boundaries, which are mountain-building events. These deposits are characterized by quartz, plus or minus carbonate veins and breccias, located in lower-order structural traps, such as veins, faults, shear zones, and fold hinges, often near major crustal faults. What are orogenic gold deposits? Orogenic gold deposits typically form at variable crustal paleodepths, ranging from less than 5 kilometers to over 15 kilometers, but most commonly at around 5 to 7 kilometers. And fluids, as well as the oroforming processes for orogenic gold deposits, remain a subject of debate. There are two main theoretical frameworks. The temperature of the oroforming fluids is also variable, but can reach up to 650–700 degrees Celsius. It's typically around 350 degrees Celsius. Studies have shown that metamorphism of peritic, carbonaceous sedimentary rocks can generate more fertile fluids than mafic rocks. The presence of CO2 itself is not always a reliable exploration guide, as it is found in both mineralized and barren quartz. However, enrichment of CH4 and H2S in gold-rich veins has been observed, suggesting a correlation between these reduced carbon and sulfur compounds and gold precipitation. While alteration is not systematic, it depends on the chemical gradient between the fluid and the host rock. Recent research, particularly from China's Jiaodong mineralization belt, provides critical geological evidence supporting this model, with PBHGS isotopes indicating enriched lithospheric mantle sources and subduction-related degassing processes. For instance, studies have identified complex overprinting of Permian-aged porphyry systems by what appear to be orogenic veins. Other typical metals and elements found in these deposits include S, B, Bi, S, B, Te, and W, generally with low base metal content. The fluids involved are typically aqueous carbonic, metamorphic fluids injected during multiple seismic cycles, with a CO2 content of 5 to 20 mol% and salinity of 3 to 7 Wt%. Traditional tools like lithological and structural mapping, geochemistry, and geophysics are now complemented by advanced technologies. These advancements have enhanced the precision of metallogenic chronology from the million-year to the 10,000-year scale, allowing for unprecedented insights into material sources and migration mechanisms. Orogenic gold deposits are a significant source of gold mineralization. It's typically found in metamorphic terrains that span from the Paleorcene to the Tertiary. This requires a range of techniques and advanced geological expertise. The recognition of gold's heterogeneity has presented challenges, but also opportunities in identifying gold from specific deposit types. Research indicates that compositional characteristics of hypogene gold particles are generally preserved during transfer to the surficial environment, supporting methodologies based on detrital gold as an indicator mineral to distinguish between mineralization types. These techniques are crucial for characterizing mineral paragenesis, or mineral associations, detailed geochemical properties, and fluid metal sources. This concept views mineral deposits as expressions of large-scale earth processes that focus energy and mass transfer across nested scales. It emphasizes focusing on the physical processes of ore formation, which are narrower in range than chemical processes, thereby enhancing predictability in data-poor environments compared to traditional analog deposit models. This means that large parts of a vein system might be barren or low-grade, interspersed with smaller, high-grade volumes. Mitigating this effect often requires advanced structural and 3D geometric modeling. Collaborations between academic researchers and industry are particularly valuable in providing insights for characterization. Their formation involves complex interactions among hydrothermal fluids, structural controls, and host rock chemistry, and quantitative analysis of pressure-driven, phase transitions, and adsorption kinetics and sulfide mantle fluid coupling mechanisms. A notable challenge in exploring and estimating resources for orogenic gold deposits is the ***Cuggett effect. ***, which describes the heterogeneous distribution of gold grade, the contested source of gold and fluids despite their economic significance, the exact sources of metals, metamorphic fluid model. This model suggests that gold is released through the phase transition of pyrite to pyrite * within metamorphic rocks as temperatures increase. Mantle fluid model ***. This alternative model attributes ore-forming materials to subducted plates or the lithospheric mantle, with supercritical fluids driving metal migration under non-equilibrium conditions. While CO2CH4H2S NACO-bearing fluids are widely accepted as present in orogenic gold systems, the source of volatiles like CO2 is still debated, sometimes interpreted as originating from the lower crust or mantle. The dynamic nature of the Earth's crust, especially in mobile belts, frequently results in different deposit types, spatially overlapping or overprinting each other, which can make understanding an individual deposit challenging. Advancements in research and exploration, characterizing gold mineralization from an early stage, is crucial for successful exploration. Project development and mining productivity, particularly for complex deposits. The field of orogenic gold deposit research has seen significant growth over the past 3 decades, evolving through distinct phases. Theoretical foundation, ***, focused on basic geological concepts and understanding tectonic controls on fluid migration and mineralization, establishing foundational classification systems like that proposed by Groves et.al. ***, technological integration, emphasized tectonic settings, fluid sources, metal migration, and isotopic tracing techniques. Paradigm breakthrough, ***, marked by a focus on the origin and evolution of ore-forming fluids, mineralization, timing, and spatial modeling. Driven by the widespread adoption of microanalytical techniques like laser ablation, inductively coupled plasma mass spectrometry. Modern exploration heavily relies on multi-method approaches and diverse datasets, remote sensing, satellite imagery, hyperspectral data, and high-resolution light detection and ranging data, often analyzed using geographical information systems or stress modeling packages. Portable geochemical analysis ***, tools such as portable X-ray fluorescence, instruments in near-infrared, shortwave infrared spectrometers for real-time field analysis, microanalytical techniques, scanning electron microscopy, cathodoluminescence, electron backscatter diffraction, energy dispersive spectroscopy, backscattered electron imaging, mass spectrometry, electron probe microanalyzer, secondary ion mass spectrometry, and X-ray computed tomography. Machine learning, increasingly being developed for interpreting complex and multi-scale datasets. It's particularly useful for exploring buried deposits that may only have subtle surface expressions. Studies on alluvial gold also play a role. This detailed characterization of alluvial gold can aid in targeting hard rock gold deposits and interpreting soil sample data. The mineral systems approach is a key organizing framework for predictive exploration targeting future directions. Despite significant advances, critical questions persist in understanding and characterizing gold deposits, leading to new avenues for fruitful research. Future studies are recommended to focus on cross-scale mineralization mechanism studies. This includes numerical simulations of supercritical fluid phase behavior, ***, four-dimensional visualization reconstruction of lithospheric material cycles. Technological and methodological advancements, emphasizing the development of AI-powered three-dimensional ore body prediction models, ***, and the establishment of deep exploration technology. Consortia capable of penetrating up to 8 kilometers. Theoretical paradigm shifts ***, promoting the integration of micro-area isotopic tracing techniques with deep, dynamic models to elucidate the control mechanisms of supercontinent cycles on the spatiotemporal architecture of mineralization systems. The field is actively transitioning from empirical exploration toward a more theory-driven research paradigm, aiming for a fundamental transformation in deep mineral exploration from empirical statistical models to process-driven models.
Are you passionate about geology and earth sciences? Explore geology with me on YouTube. Subscribe, like, and share my content.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.